Okay. You ready, Keiko?
Yeah, I think
Okay. Great. Hello, everybody. Welcome to the defense of Keiko Nagami. You all know me. I'm Max Schwager. I'm Keiko's advisor, and I'll say a few words, which is traditional. So Keiko's been working with me and many of you as well since 2019. And we were just talking about how it's been a super eventful journey. There was first COVID, which was, I don't think we even at the time recognized the sort of social and psychological impact that would have, but it was major. And through that event, Keiko pushed through and kept producing innovative work and pivoted from more experimental work towards more simulation-based work. And then COVID opened up. The world opened back up after COVID, and she went right back to experimental work and is now doing some of the most cutting-edge work at the interface of drone autonomy and vision-based autonomy. Now, one thing that I think has tied all of Keiko's research together was formulated early on in one of her first works, where, back in 2019, 2020, RL, reinforcement learning, was all the rage. People were showing incredible things in simulation with RL, and Keiko thought, well, great, we're going to solve drone autonomy with RL. So she had a state-of-the-art simulation, which she had built together with folks at Microsoft Research, and she said, great, we'll just pump in the latest RL algorithm, and doesn't work at all. Not even close. Nowhere even close to working. The drone doesn't even get off the ground. And I think that was a big realization that when it comes to drone autonomy, when you have complex dynamics, when you have stability issues or lack of stability, you need feedback at multiple levels. Pure database learning is not enough. You need to infuse lots of other tools to bootstrap the learning and to deal with the limitations of data by covering it with the advantages of model-based techniques. And that's basically the theme of what Keiko's research has turned out to be, is understanding that limit of data-based learning for drone autonomy and then covering the gap with model-based techniques. And you'll hear all about some super creative work that she's been doing over the past few years. So Keiko, please take it away.
All right, cool. Thank you, Mac. Okay, so I guess we'll get started. So hi, everyone. My name is Keiko Nagami, and today I will be presenting my thesis, Algorithms for Data-Constrained Robot Learning. Okay. So in recent years, foundation models have become much more widely accessible, especially in the form of large language models and vision language models. And while this can largely be attributed to various improvements in neural network architectures and training paradigms, the contribution that I want to focus on today is on internet scale data and how a lot of these models have access to seemingly infinite examples of language sequences as well as images. Shifting over to robotics, this is not necessarily the case in a lot of our robot autonomy scenarios. So instead, a lot of companies will have to deploy fleets of robots into the environment in order to go and collect the data that they need in order to perform these sort of learning-based techniques for robot autonomy. However, not all applications for robotics are going to be able to afford to deploy so many robots into their environments. So we might think of a scenario like needing to travel to other planets, the ocean floor. Of course, these environments are pretty difficult to actually get to, let alone deploying a bunch of robots there. We also can think of disaster relief scenarios like wildfires. So these environments can be highly unpredictable and don't really occur on a regular basis. So why use learning-based techniques in robots anyway? So there are two big benefits that these methods can provide. So one of them is that they can provide pretty fast queries and bypass expensive optimization problems as well as search algorithms. And this is especially true if you're able to keep your models or your learned models quite small. Another benefit is that they can handle more abstract input data forms, such as language and images. So an example of how this might look on a robot, you might feed a bunch of data to your robot in the form of images and labels of what's contained in those images. And you train your model. And then from there, you can input an image and ask like what is in this image, and it could tell you, oh, it's 95% sure that there's a dog in here. So this is pretty cool. However, there are a few drawbacks to these types of approaches. One of them being that because they rely on data sets, if you have a limited amount of data and you have these pockets of sort of unknown space, you can develop these out of distribution regions where your model won't know what to do with the inputs. Then another drawback is that they can also be quite difficult to interpret. So understanding why it thinks that it's 95% confident or why it thinks that there's a dog in there can also be difficult to understand. On the other side, we have more traditional model-based methods in robotics. These are more easily interpretable as they use states like the robot's position and orientation in the environment. They can also perform optimization methods without relying on data, so they can kind of just be deployed straight away instead of having to do this initial phase of data collection. However, as we mentioned in the previous slide, there are some drawbacks because these optimization problems can be slow, and this can be especially prohibitive in cases where our applications are really time sensitive. It's also unclear how exactly to reason about language and images as well, and there's also this model mismatch that occurs. Because we prescribe models to our dynamical systems when we apply these optimization-based techniques, if these models don't match what happens in the real world, which is very often the case, we'll see a little bit of an offset from what we observe in simulation versus the real world. Okay, so in my thesis, my goals are to kind of take both of these methods, both model-based and learning-based methods, and try to get the best of both worlds to try to overcome these issues of having limited data. So my thesis is divided into three main components. The first one focuses on planning and control, the second on perception and uncertainty, and the last one on mapping and semantic search. So I'll first start off with planning and control. So as Mac mentioned, in 2019, I first started working as a PhD student on this autonomous drone racing competition in collaboration with Microsoft Research. And through this competition, we were able to develop this AirSim drone racing lab environment. And I was also able to learn a lot about the state of the art in autonomous drone racing at the time. Through this competition, we kind of divided it up into three different tiers where participants of the competition received different amounts of ground truth information in order to complete the autonomous drone racing task. We had over 100 teams register and 10 final leaderboard submissions at the end. So this competition got me thinking about my own research and where I wanted to take it. So I thought about this drone racing problem as a racetrack that's parameterized by a series of gates, as we can see here on the image on the right. So what we wanted to do was break this problem up into smaller problems. So we noticed that if we could solve the problem of getting through a single gate, that maybe we could string that sort of solution through the entire racetrack in order to be able to complete the entire track. So we thought about breaking up the problem like this. And through this problem setup, there were two main approaches that kind of came to mind. The first one was Hamilton-Jacobi-Bellman methods, and the second was reinforcement learning. So Hamilton-Jacobi-Bellman approaches, or HJB, are a model-based optimal control method. They're typically solved offline before they're deployed into the environment. And this is especially beneficial because you then get a resulting policy. So a policy tells you what actions to take. So your resulting policy ends up being a lookup table. So while you're flying, all you have to do is go into the lookup table and figure out what the action you need to take is. So this process is very quick in terms of getting that best action to take. However, these methods suffer from what's known as the curse of dimensionality. And this is a phenomenon that occurs with a growing number of states in your state space because we have to solve this really big optimal control problem before we even get off the ground. So this These solution methods are often only used in really small dimensional systems and not usually seen in quadrotors. And then on the other hand, we have reinforcement learning. So this is a little bit different in that it's a learning-based model-free approach. So these methods, in our case, we'll consider it solved offline before we actually use them for deployment. So these methods, what they do is they roll out a bunch of examples of trajectories in the environment. And these trajectories then get scored. So then the behavior that's good, the behavior that gets like positive rewards, are what is tried to be repeated. And the resulting policy is often a neural network, and this is the case that we're going to consider in our work. However, a downfall to this approach is that it can require quite a bit of data, especially if it's being trained from scratch. So going back to the related work in autonomous drone racing, what do people actually do? So people don't typically, at the time, people were not typically doing either of those approaches. What they were doing instead was applying trajectory optimization techniques. So this is kind of like a model-based optimal control approach, similar to HJB. However, the optimization problem is much smaller, so it's only on the scale of a single trajectory. So you're only trying to find that single trajectory for your current time step. However, like I mentioned in like the beginning of this talk, this means that you have to be solving that optimization problem while you're flying. So you're not able to use that convenient lookup table or this neural network policy in order to find the action that you want to take. So again, talking about HJB methods, some of the work in this space largely use smaller dimensional systems like what's shown on the right or the left. And in the case where they did use higher dimensional systems like quadrotors, they typically focused on pretty small domains where they were trying to maintain a hover. And then on the side of reinforcement learning, at the time, reinforcement learning had been applied to autonomous drones. However, in order to get these systems to work, the authors needed to introduce a lot of innovations in terms of parallelization of rollouts, as well as methods to cover the state space in order to make sure that a lot of the environment was being observed. And in our contributions, what we want to do is implement reinforcement learning by initializing it with Hamilton-Jacobi solutions. So how we actually go about doing this, we break this up into a multi-stage approach. And at the end, what we hope to obtain is a neural network policy that can give us fast control updates. So what we actually do is we first solve an HJB optimal control problem, and this solution results in a lookup table. So this is what I was mentioning before. And then from there, we use that lookup table as data in order to train a neural network model in a supervised fashion. So once we have that supervised learned model, we can then have this initialized network that can have reinforcement learning applied to it. So how we actually go about solving this HJB problem. So because I mentioned these HJB methods suffer from this curse of dimensionality, we need to approximate the system as a point mass, so a much lower dimensional system. So these are the dynamics that we consider. We have our control, our drag, and gravity term. And we also have a 6-dimensional state vector, which is shown here. So this is much smaller than what is typically used for a quadrotor model. Quadrotor models typically use at least 12-dimensional states. So this is half of that. So then from there, we also need to define our cost function. So our cost function, we define in this discretized space. So here you'll see that space, especially the space surrounding the gate. So what we want to do is really get through the gate and not hit the sides of the gate. So we define our cost function as having a low cost by getting to the center and a high cost of hitting the sides of 0 and 10 respectively. And then we also have a term in our cost function that tries to get us to get to that target set as quickly as possible. So that's that second term in the cost function. Once we discretize the environment and solve for a HJB lookup table using value iteration, we can then use that lookup table and perform a k-nearest neighbors interpolation to increase the number of state action pairs that we want to learn from and minimize a Huber loss in order to perform supervised learning on a neural network policy to try to match the outputs in that lookup table. So from here we have a neural network that has been initialized using that HJB solution. However, we'll note that all of the solutions that we've obtained so far are using that lower dimensional system. We have no notion of this higher dimensional system yet. So this is where we incorporate it in our reinforcement learning stage. So here we perform rollouts of the drone's trajectory through the gate, and we use the 12-dimensional quadrilateral model here. And we also use a curriculum learning style approach where we initialize the states of the trajectories to be in some really small region in front of the gate. So initializing it right here is pretty easy to get through the gate. And then we slowly increment this region of the state space to make the problem a little harder, and so on and so forth. So then finally, we test our method in a simulation environment that we shared at the beginning. So here we have a racetrack where this is a top-down view of our environment where we have a trajectory of the drone's progress through the gates, as well as the drone actually progressing through that simulation environment racetrack. And we find that our drone's able to make it through the full track. Okay. So then we compare our approach to 4 different baselines. So we compare our method against just using that supervised learning stage from our pipeline, so it's more of an ablation. The second is we compare against a trajectory optimization approach. So this is the more traditional method at the time of solving that optimization problem while flying. Then we have an HJB lookup table and a reinforcement learning approach. And again, this reinforcement learning approach used only vanilla policy gradient, and we found that we were not able to get the drone to really get through the gate at all. And this is not so surprising considering the amount of innovation that a lot of the other prior work needed to add to reinforcement learning in order to get their systems to work for quadrotors. And we find that our method is able to have the lowest average race time here. So we might notice that none of these experiments in this first section of our talk occurred in the real world. This was all in simulation. And as Mac mentioned, this is largely due to the fact that this work took place a lot of the time during COVID. So we wanted to think about how we could actually move on to hardware at this stage. So one big step was incorporating perception and estimation. So these 2 modules really allow us to understand where we are in our environment. And this is especially important if you don't have access to things like GPS and motion capture systems. So this is what we wanted to consider. And at the time, it had become quite popular to use a learning-based module in our perception stack. So we tried this. We tried implementing a learning-based approach to try to go from images to our ego pose. However, we had a lot of difficulty with this and feeding this information straight into our HJBRL policy. And this is largely because neural networks can be quite susceptible to error. And this is what we wanted to focus on for the next piece of the talk. So this error not only affects the single perception model itself, but this error can propagate through the entire autonomy stack, especially because they're all so tightly knit together. So what we wanted to look at was trying to mitigate these unreliable outputs so we could avoid these dangerous scenarios. So this leads into the second part of the talk where we focus on perception and uncertainty. So there are 2 main types of neural network uncertainty. So the first one is aleatoric uncertainty, and this comes from inherently noisy training data. So if you think about an example where you're collecting a bunch of data with a microphone, and say you care about the sounds that different kinds of birds make, and you're trying to train a model that, given like a bird sound, it'll tell you which bird it is. And you train your model, however your data was taken on some rainy days, some windy days, etc. So this extra noise in the background can contribute to this aleatoric uncertainty. On the other hand, we have something like epistemic uncertainty. So this stems from a general lack of training data. So it appears in out-of-distribution operating regimes. So going off of that same example, if we then take that same model and try to apply it to insect sounds, we can't assume that this model is going to work well, because all of these inputs are going to be out of distribution. So while aleatoric uncertainty can be learned as a distribution to a random variable, since we have access to that noisy data, epistemic uncertainty is a little different in that we can't necessarily learn and quantify it because we don't actually have access to that missing information yet. So the goal in this part of the talk is that we want to quantify our neural network perception system's epistemic uncertainty, and we want to navigate to regions in our environment that will give us low uncertainty while still trying to achieve our goals. So this sort of problem setup creates this new challenge where we actually have to anticipate the perceptual uncertainty at future states, even though we're not there yet. So we might picture this like we have a drone here. Our drone is at state x naught, y naught, and it's currently time t equals 0. And we can only take an image right here, right now. But what we really want to know is what are we going to see in the future, and how good are those measurements going to be? And based on that, which path should I take? But a lot of the existing methods in quantifying epistemic uncertainty assume that you already have access to this image. But we don't assume that because we're trying to do this predictively. So going back to this autonomous drone racing related work, this paper, this Beauty and the Beast paper, while they performed trajectory optimization on the planning side, they actually use the neural network for their perception side. And they go specifically from images to ego poses. And this is exactly the type of setup that we wanted to do. And they also reason about uncertainty in this work. However, they focus much more on this aleatoric uncertainty. On the other hand, what we want to do is think about epistemic uncertainty. So there is quite a bit of work done in this space. One method is known as ensembling techniques, where you train a series of neural networks on the same data, see where they agree and disagree, and where they disagree is kind of where you have that epistemic uncertainty. And there are also methods that use Fisher information on the parameters of the models that you train. However, these methods both often assume that you have access to that input already, which we're not trying to assume that we have. On the planning side, our goal is to be able to navigate to regions of our environment with high certainty, so that we can be certain about where we are so that we can get to our goals. So a lot of these systems, when they are shown as examples, are shown in these light-dark domains. So these light-dark domains are shown here, where you have this dark region of your environment, and this is supposed to represent like the lights being off. So your measurements are not going to be very good. You might not really know where you are based off of them. Whereas in this light region, the lights are on, your measurements are great, and you can really figure out where you are. However, a lot of these light-dark domains, all of them are considering aleatoric uncertainty. So in our work, what we want to do is bridge this epistemic uncertainty quantification approach with beliefs-based planning. So how do we actually go about quantifying epistemic uncertainty? So we first train a neural network image generator that looks like this, and we then train a second model that looks like this. So this is a neural network perception model. So you'll notice that these two models are really the inverses of each other. One goes from the ego pose of the drone to try to generate an image. The second goes from a ground truth image to try to figure out where the drone is, that ego pose. So these two models can be trained on a similar data set. We can then use the composition of these two models to get the difference between that input z and this output z hat in order to get an epistemic uncertainty signal that allows us to have access to it before we actually have access to this image here. So the way this looks is just feeding forward a query pose. So you might see it's some XYZ coordinate. What would I see? So it would generate an image. If you've never been there before, that image is going to be really poor. Then that poor image is going to go through this perception model, and then you can't really expect this z tilde to match that input very well. So then this difference will be really large, which is exactly the kind of behavior that we're looking for. Okay. to be more specific about how we reason about or how we represent our states, we use Gaussian belief dynamics and a Kalman filter for state estimation. So we represent our state as a Gaussian distribution, which is represented over here. So this is really focusing on the ego pose of our drone, and we parameterize it as a Gaussian distribution with a mean and covariance. So you might have some notion about where you think you are, and this estimate might look like this distribution here. And then what we do is process a prediction step. So this prediction step takes into account our dynamics model of the system. So what we think the drone is going to do. So this, once we incorporate the dynamics model, we can get an updated notion of where we think our state is. We can then further also incorporate the measurements that our drone is receiving at test time to further kind of adapt our current notion of where we think we are. So this distribution changes depending on these sorts of this information that we're gathering. And this can happen in a loop, because you're always moving and you're always getting this measurement data as you're flying. And in our work, what we want to do is really focus on this measurement piece. And specifically what we want to focus on is this R matrix, which represents how confident we are in the measurements that we're getting. So to dive a little deeper into our approach, we again have this prediction step, which is really focusing on our dynamics. From there, we're sampling from that predicted distribution of where we think we are. We then generate from those samples a bunch of simulated images and then try to come back down into these poses, like I mentioned 2 slides ago. We then take an error between that input and output to get a measurement uncertainty matrix. And this is what's fed into our update step. So this tells us how confident we are about the measurements that we're receiving. So how does this look in a beliefs-based planning approach? So we demonstrate our method in a domain shown here. So this is a top-down view of a region where a drone is flying and is trying to get to this goal. So this domain in the background, this little heat map that's shown, is an epistemic uncertainty sort of heat map. And the way we create this is that we withhold any training data from this side of the environment and only train our models from images and poses that we receive over here. So we have large epistemic uncertainty regions over here. So we initialize our trajectory. It's kind of like a straight line to the goal. And through the trajectory optimization process, our trajectory gets pushed into this light region because we want to see, get really good measurements first so we know where we are before we then go to our goal. And we'll note here that these sort of ellipses surrounding this main trajectory actually represent the confidence about those states. So when it kind of gets pushed into this lighter region, those ellipses get like shrunken up because we're more confident about where we are. That's the goal. And the actual trajectory optimization problem that we run is shown here, where we have 3 main cost terms. So the first one is to try to get to that final state with low uncertainty. The second one is to actually reach the goal. And the last one is to do so without exerting too much control effort. And all the other equations here are the Gaussian belief dynamic constraints. So we again test our method in this autonomous drone racing scenario where we compare against a method that uses this aleatoric uncertainty representation for the uncertainty metric. And we find that our method is able to maintain a state estimate that's much closer to the ground truth state while also being able to get through the racetracks faster. So again, we're still in simulation. There are a few reasons why we can't directly apply a lot of these methods in the real world. So one of them is that rendering quality. So you might have noticed in the previous slides, the renders were pretty fuzzy, and they actually require thousands of data points in order to even get that image quality. So in 2023, 3D Gaussian splatting had been introduced in the computer vision community, and a lot of people had been adapting it to robotics applications as well. So this is a video of a render. So these are not real images. These are rendered views. And we can see that they're extremely photorealistic and taken in the real world. And notably, these only take orders of like like 100 or so images to train on, as opposed to the quality that we were receiving here that required thousands of images, and we were still getting pretty blurry images. And this is a largely 2D approach where we're only feeding in those images and expecting to get this 3D pose from it. However, Gaussian splats use 3D information, which gives it so much power. So what they do is they parameterize the environment as a bunch of Gaussians or ellipses, and each of these Gaussians has mean, covariance, opacity, and color, and we're able to then, from a new viewpoint, render all of that information. So we want to incorporate this technology into our follow-on work. So how we actually do this, so this is a 3D Gaussian splat of our flight room in the basement of this building. And we intentionally created this large piece of high epistemic uncertainty, which is shown in this darker cloud over here. So really, this darker cloud represents a lack of training data in our Gaussian splat. So an application for this is if someone else collects a data set for a different purpose, and then you want to repurpose that same data set for your own work, you should still be able to use these data sets, especially if they give you a good enough representation of the environment. So the goal here is not to like waste the data that has already been collected. Okay, another big bottleneck for applying these approaches to the real world is the planning approach. So in the previous section, we talked about a gradient-based planning approach. So those approaches actually took anywhere from 30 minutes to an hour to compute the solution to a single trajectory. And this is because we incorporated the parameters of those neural network models into our gradient-based planning problem. But here we want to apply a sampling-based approach that could be a lot faster. So this is an example of a trajectory that is generated through this domain, where we have our drones starting off facing the unknown region of the environment, this high epistemic uncertainty, and then the trajectory then gradually guides the drone to face into that known region of the environment, so it could get that good data that it can get a good state estimate on. So how we actually go about performing this sampling-based planning approach, we have a few stages. The first one is that we initialize these distributions on each of the state differences along our nominal trajectory. From that distribution, we then sample. And then we can score these sample trajectories that might not necessarily be dynamically feasible. From there, these high scoring trajectories, we do a trajectory smoothing approach to try to get the dynamically feasible equivalent trajectories. And then we shift that initialized distribution over to kind of center around those higher scoring trajectories. And this is done in a loop. So this distribution will slowly kind of converge into like a smaller covariance, and the trajectories themselves will become higher and higher scoring. Okay, so we compare our approach to two different baselines in a simulated environment. The first baseline uses this Fisher information metric approach, and we find that our method is able to maintain a lot faster of a replanning time. The second baseline that we compare against samples directly in the control space, so it doesn't perform that trajectory optimization step. So it's a little bit faster. However, we find that our method is able to maintain a much better trajectory goal cost as well as a trajectory uncertainty cost. So then we finally apply our method in the real world. So we have our drone and it's facing into that high epistemic uncertainty region that we were showing before. And then as the planner is running, it kind of pushes the drone into turning around to facing that high certainty region of the environment so that it can get a good state estimate. Okay. So the second part of the talk really all focused on the ego pose of the drone. So now we want to shift gears a little bit and think about the world around the drone and how we want the drone to really, or the robots, to interact with the world around it. So for example, you might task your robot with something like find the tree. So in this language instruction, how can we ask our robots to explore their environments without necessarily having access to an initial map? So even if you do have an initial map, maybe it looks like this. So obviously there's no tree in the environment. So what we have to do is get our robots to figure out how to explore the environment so that they can build that map, so that they can gain the data that they need, and then also search for the object that's being queried for, and ultimately find the tree. Okay, so this leads into our third part of the talk, which is mapping and semantic search. So just to reiterate, our goals here are to create a high fidelity reconstruction of our environment, and we also want our robots to actually achieve their goals, like get to the object that's being queried. So the related work in this field, in 2023, this paper, Clip on Wheels, was published. And this paper, along with many other approaches, break this problem down into two different subproblems known as exploration and exploitation. So exploration really focuses on this problem of completing the map, really figuring out everything that's in your environment and having a good reconstruction. The second part is that solving that task piece, so actually going to the object that's being queried for. And these approaches used a point cloud, and they also used a heuristic-based approach to switch between these two modules. And what we want to do in our work is do a little bit more of a smooth kind of comparison between these two objectives in order to achieve our goals. And again, what we'd like to do is to incorporate 3D Gaussian splatting as well. We find that because they're able to produce such high quality reconstructions of our environment, they could be really beneficial for downstream tasks like manipulation and such, so that you can really know like the surfaces of the objects that you're interacting with. And of course, we also want to leverage a lot of the work that had been done in robot exploration. However, a lot of these approaches don't use methods like 3D Gaussian splatting for their map representations. They use things like voxel grids and point clouds. So we want to kind of fuse these two concepts together. And this leads to our contribution. So just to reiterate, what we want to do is to build semantic maps in the form of 3D Gaussian splats. We want to quantify the epistemic uncertainty associated with the map, so we know which pieces of the environment need the most data. We also want to be able to develop planning approaches that can incorporate the semantic information as well as this epistemic uncertainty. And we also want to be able to do all of this in real time on real robots. So we break our problem up into three major components: semantic mapping, trajectory proposal, and trajectory scoring. So for semantic mapping, what we do is we develop this real-time Gaussian splat training method, where here you'll see in this video all of these green boxes indicate the camera poses of the drone as it's moving. So as the drone is moving, it's streaming these camera pose information, the camera pose information as well as the images. And as it's streaming, it's able to, in real time, construct this 3D Gaussian splat. So this is pretty powerful that we're able to kind of train this model in real time. And then at the same time, we also want to incorporate semantic information into this map. So we do this by leveraging OpenAI's CLIP Vision Language Foundation model. So we're able to embed the semantic information into the 3D Gaussian splat through the semantic channel that might look like this. So if you query for the wagon, we're able to get this heat map that shows exactly where things that look like the wagon might be. Okay, great. And then from there, what we want to do is port this information into a coarse voxel grid so that we can use this lighter weight map representation for fast planning. So we can port the RGB information in directly, the semantic similarity channel in directly, and then we can also leverage the geometry associated with that voxel grid representation in order to produce a geometric uncertainty metric. So this geometric uncertainty metric that we introduce is voxel-centric. So each voxel holds information about the directions it has been viewed from so far. So that's represented here in this GIF. So we have these red rays sort of representing all of the different angles that this specific voxel has been viewed from so far. So then we can quantify information gain as the coverage that new training camera view rays would provide. So if you had a bunch of rays for this singular voxel that were all like on this side of the circle, then you would want to get a new training camera view that's on this side of the circle. So you want to increase the amount of coverage here. Okay, we also need to define in our voxel grid different parts of the space, unobserved, occupied, and free space. So occupied space we get for free. So this is a top-down view of our voxel grid environment. And this occupied space we get for free straight from the 3D Gaussian splat. So we can populate that information. And from there, we need to differentiate between free space and unobserved space, because we only want our robot to be moving in free space. We don't want to send it into places of the environment that we have no idea what's there. So in order to do that, what we do is query the training camera views, cast rays into our environment to see where they intersect with this, with these occupied voxels, and any of the voxels that they traverse through on their way to those occupied voxels is considered free space. And this is kind of intuitive because if I can see the table from here, that means all the space in between is free space. Okay, so now that we've reasoned about what our free space is, we can then perform some planning. So this is a top-down view of our environment where we have our drone at the star, and it's trying to generate some sampled plans. So the way that we actually sample is we instantiate a Gaussian mixture model. And this Gaussian mixture model allows us to sample from this distribution so that we can bias the trajectories toward frontier voxels as well as high semantically similar regions of the environment. And here our frontier voxels are specifically regions of the environment that have a border between free space and unobserved space. So you can imagine if you get to those pieces of the environment, you have the opportunity to gain a lot of new information there. So these are the kinds of locations that we want to send our robot to. From there, we have a bunch of proposed trajectories, and we want to score all of the trajectories based on both the semantic similarity that they observe at each of the frames along the trajectory, as well as the geometric information gain that they're going to get. So the way we do this is we actually use the renders kind of generated like this along the trajectory and weight both of these two factors together in our final scoring metric. So we want trajectories that get to that high semantic similarity point, like the wagon that's shown in here. But we also want to be gaining as much information as we can on the way there as well. So we compare our method to do different baselines. The first one, our T-guide, is a geometric information gain only approach, so it doesn't reason about semantic information. And the second one only reasons about semantic information. So we're kind of dividing the two problems that we're trying to solve together into two separate baselines. And we compare our methods in two different maps. So the easy map is a low occlusion domain. So this is a setup where there's basically an empty room and we just place the objects in the room. And we find that all three methods kind of perform pretty on par with each other. And then we compared against a harder map with high occlusion. So in this case, we had a lot of sort of cubbies occluding a lot of the objects that were being queried for. So the robots really needed to kind of peer around corners in order to find the objects that they're looking for. So this really stress tests that like exploration piece. And we find that especially in that second harder map, our method is able to outperform the other two baselines pretty consistently. So here are some examples of our approach in hardware. So we apply it on a spot quadruped robot. So it does this initialization phase where it spins in a circle to get a smaller initial map. But we'll note that this query object is not in that initial map. So then through these two channels, the robot then needs to try to build the map and also find the queried object, which is the chair in this case. You'll see that the chair lights up and the robot stops. So we also do this in our MSL quadrotor experiments where we query for the wagon here. So we'll see that the wagon sort of lights up in the semantic similarity channel once it's able to find it. And this is the high occlusion map domain. So you'll notice that there's a lot of blockages sort of preventing the drone from seeing it right away. Okay, great. So this concludes my talk. So in summary, we had planning and control, perception and uncertainty, and mapping and semantic search. And this was all sort of, all of these pieces of the talk were considering having low amounts of data and what to do in each of these cases. Here are some of the, so at the top here are my publications that I presented today, and at the bottom are some publications that were not presented today. Okay, great. Should I go straight into acknowledgments? Okay, sounds good. So I want to thank my committee for taking the time to be here today. I want to thank Professor Allison Okamura for agreeing to be the chair of this committee. I'd like to thank Professor Okamura and Professor Mark Kokoski for the experiences I've been able to have through working with students in your lab, being able to kind of broaden my horizons as a roboticist through mounting various manipulators and gripper arms onto our MSL drones. I'd also like to thank Professor Grace Gao and Professor Michael Kokender for being on my defense committee and also being on my reading committee and really helping me to refine today's talk as well as my thesis. And of course, I want to thank Mac for being a really great advisor during my PhD. Mac really makes the time to meet with all of us and be very involved in all of our research and cheer with us in our successes and really help us through the more difficult times. So I'm really grateful to have been able to work with you. I want to thank all of my co-authors that I've been able to work with throughout the years and also recognize my funding sources. I'm grateful to have been able to work with so many smart people that I could learn from and lean on in all sorts of different challenging projects. I also want to thank everyone at the NASA Ames Aeromechanics branch. So during my time at Stanford, I had the opportunity to do a NASA Pathways internship with the branch. And I particularly want to thank Bill, Carlos, and Shanna for teaching me so much about UAM and flight dynamics and controls for rotorcraft. I also want to thank everyone at the MSL. I'm really lucky to be part of a lab that fosters so much collaboration and how everyone kind of has a different perspective on different problems. And I feel like getting to kind of work through different research problems with all of you has made me a much better researcher. I also want to thank all of my friends who have been able to tune in today. Both the friends who I've been able to make in the Bay Area and the friends that I've been able to kind of keep in contact with from home. I'd like to thank my partner Brian and our dog Papaya. I'd like to thank Papaya for always preventing me from thinking about school-related stressors by providing new stressors of her own. I'd like to thank Brian for choosing to bring Papaya into our lives and for also just being there to support me throughout the PhD, even as he worked on his own PhD. I'd also like to thank my family who is able to both tune in and be here today. I'm really grateful to have a team that's always rooting for me and really always prioritizing my happiness and making sure that that's happening. So yeah, thank you everyone. That's everything.